Okay, so let's continue. Any questions? About this time evolution operator, the generator of the time evolution operator? Question? Now let's get the energy eigenkets. Now, we don't know the Hamiltonian, so we basically don't know the energy eigenkets. But suppose we have some operator, A, that commutes with the Hamiltonian. If we have such an operator, we can talk about the eigenkets of this operator A. And we had also seen that if the eigenkets of the operator A are discrete, are non-degenerate, if they are non-degenerate, so these eigenkets should also be eigenkets of our Hamiltonian. And let's denote the eigenvalues by AI. Now, what is the Hamiltonian operator to start with? Well, we know the eigenkets of the Hamiltonian now. We had already seen that if we have the eigenkets of an operator and the corresponding eigenvalues, the operator we can always write in this form. The eigenvalue times the eigenket times the eigenbra. This is our Hamiltonian operator. Or if you want to find the time evolution operator, from t0 to t0 plus delta t, or from t0 to t1. This was the exponential of minus I over h bar h of t1 minus t0. Well, the operators, the functions of operators, we always interpret them as a Taylor expansion. So let's see, this is equal to sum over n from 0 to infinity minus I over h bar t1 minus t0 to the power n times 1 over n factorial h to the power n. Well, this is our Hamiltonian operator. So let's calculate its powers. So let's start with h squared. H squared will be sum over I, the energy of the kit AI, this is our Hamiltonian. Let me multiply it with another one, AJ. This is sum over I and J, energy of AI, energy of AJ, AI, AJ, AJ. Well, you see, this is nothing but Kronecker delta Ij, which basically tells me that when I am summing over J, I only take the terms J is equal to I. So this is equal to sum over energy of EI squared, AI. So, well, basically I could have, in fact, just wrote this out straight away because I know that HAIs, they are the eigenkets of the Hamiltonian, so they are the eigenkets of Hamiltonian squared also. And the corresponding eigenvalue is nothing but the energy squared. So this is the eigenvalue of H squared, the corresponding bra. And in general, we can just generalize this to H to the power n as an operator is nothing but energy of the ket AI to the power n AI. Now let's come back to here. our time evolution operator. U of T1, T0, this is equal to from n 0 to infinity minus I over h bar T1 minus T0 raised to the power n 1 over n factorial. Hamiltonian to the nth power is just sum over, let me use the index j, e of aj to the power n, aj. Let me just change the order of summations. This will be equal to sum over j, sum over j, sum over n from 0 to infinity minus I over h bar, T1 minus T0 raised to the power n, e of aj to the power n divided by n factorial. Times aj. You see here, this is nothing but the Taylor expansion of the exponential function. I'm sorry. aj. This is the e to the power minus I over h bar, T1 minus T0, e of aj. Sum over j, e to the power minus I over h bar, T1 minus T0, e aj. So here is our time evolution operator. So basically, we know our operator now. Of course, assuming we know the energy eigenvalues and the energy kets. And since we know the operator, we can write the time evolution of any state that we like. You see, let's assume that we have this ket alpha. At the time t is equal to t0, let me write this notation. Let's say at that time we know an expansion of it in terms of the energy eigenkets. Now alpha at the time t is nothing but alpha at the time t is equal to t0 and evolved from t0 up to the time t. Well, we know the evolution operator, sum over j, e to the power minus I over h bar, T1 minus T0, EAJ, AJ, AJ alpha. Of course, this alpha is at time t is equal to T0. But if you look at this one, take its inner product with AJ, you just get CJ, the coefficient. Now this is I, sum over I. This is just my CJ. This is sum over J, e to the power minus I over h bar, T1 minus T0, e of AJ, CJ, AJ. Well, you see, if you compare it with at the time t is equal to t0, now if you have your ket, if you expand it in terms of energy eigenkets, the time evolution is quite simple. just insert this exponential at each one of those terms. Or you can say, let's say, alpha at time t, we can just write it as, at any time t, we can always write it as an expansion in terms of aj, but the coefficients will be time dependent in general. If the eigenkets are energy eigenkets, Cj of t is just e to the power minus I over h bar, t minus t0. So this t1 is just t, Cj of t0. So time evolution only causes these coefficients in the expansion in terms of the energy eigenkets to acquire a phase. You see, Cj of t the magnitude does not change. Of course, this is only valid if these AJs are energy eigenkets. In general, this will not be satisfied. Any questions? Let's look at how the expectation values change in time. So we know how the states are changing in time. What about the expectation values? You see, let's just assume that B, time dependence of expectation values. B is some observable, and it doesn't necessarily commute with the Hamiltonian. So let's look at the expectation value of B in this state alpha. Well, we said that this is equal to alpha at the time t, B, alpha at the time t. Let's look at this one. The state is evolving. So the operator, its expectation value will be a function of time. This is equal to, well, this alpha of t, we had already calculated it. This is sum over j e to the power minus I over h bar. So here I forgot an EAJ. T minus, well, let me also choose T0 to be 0 for simplicity. Minus I h bar T EAJ. AJ. This is my kit. The bra is just a dagger of that, and that would be sum over I e to the power I over h bar T EAI AI. And of course I also have CI star over here, CJ over there, the expansion coefficients. This will be equal to sum over IJ Ci star Cj e to the power minus I over h bar T EAJ minus EAI times AI B AJ. So you see, in general, the expectation value of B will also depend on time. So what are the cases under which this expectation value will be independent of time? So let's just assume Ci is equal to 1, Ci0 is equal to 1, and Ci is equal to 0 if I is different than I0. So basically, I'm assuming that my ket alpha at the time t will be e to power minus I over h bar t EAI0 AI0. It's an energy eigenket. It just only has this one with a phase. Now, if you look at this expression, only the I is equal to I0 and J is equal to I0 term is non-zero. But for that term, this difference is just 0 because J is I0, I is also I0. We are talking about a single state. There is not a sum, there is just a single term in this sum. And this is just 0, e to the power 0 is just 1. So in this case, B alpha as a function of time is just AI0, B AI0. So you see, it's independent of time. So if you start with an energy eigenket, the expectation values do not change in time. In that sense, we say that the energy eigenkets are stationary states. They do not change in time. In the sense that if your system is in this ket, nothing changes. All the expectation values are the same. In principle, it will be time dependent. We didn't impose the condition that it should be time independent. But what we know, what we have seen is that if the state is an energy eigenket, it's a stationary state. So it doesn't change in time. It just turns out to be independent of time. And the expectation values are independent of time, not because of some property of B. You see, we will later on see that B might be a conserved quantity, for example. If B is conserved, maybe it doesn't change because of that. But we started by saying that, well, we will see later on that if B and H, they do not commute, then B is not conserved. And not necessarily B is a conserved quantity. Nevertheless, in these states, their expectation value does not change. So we know that this fact that the expectation value in these kinds of states do not change is a consequence of the fact that these are energy eigenstates. Not because of the property of P, but because of the properties of these energy kets, that those expectation values do not change. Okay, yes. But the superposition is not. You see, here I'm not talking about any superposition of these. Each one separately is a stationary state, but their superpositions are not. Only if we have an energy eigenstate, then it is a stationary state. So let me write. A stationary state is an energy eigenstate. Their superposition of energy eigenstates is not an energy eigenstate, not necessarily. So it is not a stationary state. Let's do an example. Suppose we have this Hamiltonian. Let's say it is minus mu dot p. Mu being the magnetic dipole moment corresponding to spin, b is the magnetic field. And I will assume that b is constant in the z direction. So the Hamiltonian will be minus mu z times B. Well, mu z is, let's say, the charge divided by times h bar divided by twice the mass of the electron multiplied by the z component of the spin. Times B. Or let me write this in this form, minus mu B S Z. Mu B S Z. Mu being this combination of constants. This is my Hamiltonian. What are the corresponding eigenkets? No, mu s is not an eigenket. You see, H is proportional to Sz. An eigenket of Sz is also an eigenket of H. So we have these two eigenkets. Plus, Hamiltonian acting on plus just gives me, sorry, this H bar is not over there, the H bar is over here. It just gives me minus mu B H bar over 2. Plus, and H acting on minus is plus mu B H bar over 2 minus. So these plus and minus states are my energy eigenkets. Let me give them some names. This is equal to E minus E over 2 plus. Let me call this E over 2 minus. E being mu B H bar. This is how I define it. Now let's assume we have an arbitrary state. A plus B minus. This is at the time t is equal to 0. Then I can just straight away write what the ket of my system at the time t. You see, we had already seen that at the time t, the state is, you just multiply it with those exponential phases. Of course, assuming that we expand in terms of energy basis. So alpha of t is a times e to power minus I over h bar t times minus e over 2 plus b times e to power minus I over h bar t plus e over 2 minus. This is my ket at the time t. Let me look at my Sz expectation value. Well, this is nothing but alpha of t Sz alpha of t, or let me write it in this form, sum over alpha of t. My Sz operator is h bar over 2 plus minus alpha of t. This is equal to h bar over 2 plus alpha of t absolute squared minus h bar over 2 minus alpha of t absolute squared. This is equal to h bar over 2. So you see, this is nothing but that coefficient over there, a squared, minus h bar over 2, b squared. So you see, although I didn't, even if A and B separately, they need not be 0. None of them need to be 0, so it's not a stationary state. You see, if A is 0, it's a stationary state. If B is 0, it's a stationary state. But A and B, if they are not both 0, it's not a stationary state. Nevertheless, the expectation value of SZ is independent of time. That is basically because the Hamiltonian commutes with SZ. So that's why basically we still have the expectation value of SZ is independent of time because the Hamiltonian commutes with SZ. Now let's look at the expectation value of Sx. Do you remember what Sx operator was? This was our Sx operator. So let's look at the expectation value of Sx operator. Well, this is equal to, in the state alpha. This is equal to alpha of t, h bar over 2, plus minus, plus minus plus, alpha of t. This is equal to h bar over 2, alpha of t, plus minus alpha of t, plus alpha of t minus plus alpha of t. Well, I will not just calculate those terms separately. You see, if you just take the complex conjugate of that term, well, this just becomes this one, this becomes this one. So the second term is the complex conjugate of the first term. So this is equal to h bar times the real part of alpha of t plus minus alpha of t. Well, let's remember what the alpha of t was. This was our alpha of t. This is equal to h bar times the real part of, well, alpha of t plus is just the complex conjugate of that term over there. And that gives me e to the power minus I over h bar t e over 2. It is this one. Well, why the complex conjugate? You see, alpha is the bra, not the ket. So to convert it into a bra, I have to take the complex conjugate of that one. If you look at this one now, alpha is a ket. I'm multiplying it with the minus state. That gives me the coefficient of that minus state. Well, it basically is exactly the same term. Sorry, I have some coefficients. Here I have the A star. Here I have the B. Minus I over h bar t e over 2. So the expectation value of Sx is nothing but h bar times the real part of a star b e to the power minus I over h bar t times e. Now we can look at a particular case. Now in general, A star, yeah, okay, one thing, if, again, both of them are non-zero, A and B, they are both non-zero, then you see that the expectation value of Sx has a time dependence. It depends on time. If one of them is 0, that in that case we are talking about a stationary state, either A or B is 0, we will have a stationary state. But in that, we had already seen that in general, in stationary states, the expectation values do not change in time. Well, you see over here, if A or B, if any one of them is 0, this is 0, the expectation value of Sx is 0, independent of time. Now let's look at a case when we have, for example, an SX state. Let's assume that alpha at t is equal to 0 is actually an Sx plus state. Well, this basically tells me that A is equal to B is equal to 1 over square root of 2. So in such a case, Sx will be h bar times the real part of 1 over 2 e to the power minus I over h bar Te. But this is h bar over 2 times cosine E over h bar times T. So this is the expectation value of the Sx operator in a state that started out to be an Sx eigenstate, but it is subject to a magnetic field in the z direction. Now let's also look at the Sy. Do you know the Sy operator? Do you remember it? You see, this was our Sx operator. Do you remember our Sy operator?
Only the I difference measurement.
It is I times h bar over 2 plus minus 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 plus. Well, if you just go ahead and calculate the expectation value of Sy, I think there was a minus also over here. You see, what will happen is, if you look at the top two lines, this is a minus, we have a minus I over there. So again, those two are just complex conjugates of each other. So we have a number minus its complex conjugate just gives me twice the imaginary part. So instead of this expression over here for Sx, where we took the real part, Sy will be just h bar times the imaginary part of alpha of t plus minus alpha of t. And so it will be h bar times the imaginary part of a star b e to the power minus I over h bar Te. And again, if you look at the case alpha at t is equal to 0, is equal to Sx plus then Sy is just h bar times the imaginary part of 1 over 2 e to the power minus I over h bar t times e. This is h bar over 2 times sine e over h bar times t. And, well, Sx expectation value squared plus Sy expectation value squared, it just turns out to be h bar squared over 4. Well, you see, if you just look at these, the Sx expectation value, Sy expectation value, well, the spin is basically rotating around the z-axis. These are the expectation values. And the frequency is nothing but E over h bar. E being the energy difference. So this is in general a general property of non-energy eigenstates, non-stationary states. When you look at the expectation value of an operator in a non-stationary state, you see here, the above line, you see that the expectation value is basically a sum over terms that are oscillating with frequencies given by the energy differences divided by h bar. That's a general property in quantum mechanics. spin per session, not spin flip really. SZ stays the same. It doesn't. Flip usually means if you start with SZ plus, it becomes SZ minus. Well, this is spin flip in the x direction. You start with Sx plus, after some time you end up having Sx minus. Now, you see, up to this point, we haven't been talking about any differential equations, solutions of differential equations, etc. Nevertheless, with very simple mathematics, let's say, just we are working with energy, with some Hilbert space, we are talking about some operators. Nevertheless, we can just study some significant phenomena. Any questions? So, where did I lose you? We can go back. Shall we go over what we had done up to this point? And if you have any questions, you can just ask. Okay, so we started by looking at the time evolution. We said that, okay, the time evolution, we will describe it as using some kind of an operator, which just like in translations in coordinates, this will translate in time. And we had seen that to conserve probability, it has to be a unitary operator. And we also wanted it to have this property that two successive time evolutions, well, it's a single time evolution, in fact. It should be a single time evolution. So the product of two time evolutions should be, we should be able to write it as a single time evolution. In fact, this property alone tells me that it should be kind of an exponential, because the exponential has this property. The product of two exponential is itself an exponential. And we also said that no time evolution is no change in state, so it should be identity. And then we said that, okay, so let's look at very small time evolutions. And if the evolved time is very small, we can consider a Taylor expansion in terms of dt, and the coefficient, I just call it minus I times some operator, h omega in this case. Well, why did I insert that minus I? Mathematicians do not insert it. They don't really care about Hermitian or non-Hermitian or anti-Hermitian operators. For us, we like Hermitian operators, so we know the answer. I know the answer that this, whatever appears as the product of dt should be an anti-Hermitian operator. So if I just factor out the factor of I, it becomes a Hermitian operator. So by putting this minus I, I'm making sure that omega turns out to be Hermitian. It is a direct consequence of the fact that U should be a unitary operator. If U is a unitary operator, in its Taylor expansion, the coefficient over here multiplying minus I dt should be Hermitian. And it automatically satisfies this property that the product of two evolutions is a single evolution. And then, of course, there was the question is, what is this operator? Well, this is an operator, as your friend has pointed out. It has an operator that has the units of inverse time. It's multiplying time. So it's a frequency. Well, a frequency is E over h bar has the same units of frequency. The energy is, in classical physics, we usually talk about the Hamiltonian. At least in most relevant systems, energy is just the Hamiltonian. So we are tempted to identify this operator with the Hamiltonian. It also makes sense because basically the Hamiltonian in classical physics is the generator of time translation. Here this operator omega is our generator. It creates the time translation. So that's the identification we made, and it just turns out that we will later on study that this h bar should be equal to the same h bar that we use in position translation, so that we will be able to have this equation in quantum mechanics, with p and x being operators. And then there was the problem of time evolution by a finite case. Most of the time we will be dealing with Hamiltonians that are independent of time until we come to the chapter of perturbations. If Hamiltonian is independent of time, then the time evolution by a very small amount dt is independent of when you start that time evolution. So if you just divide this finite time translation into very small time translations by an amount dt, all of these operators, since they are all evolutions by this very small amount dt, they are the same. They only differ by when you start that time evolution. But by saying that Hamiltonian is independent of time, you are saying that this U operator is independent of when you start. It only depends on how long do you evolve your state. So each one of these is 1 minus I over h bar h dt, assuming dt is very, very small. Well, eventually we take the limit that dt goes to infinity, and this is our finite time evolution operator in terms of our h operator. Of course, whenever you see this exponential of some or some other function of operators, we always interpret it in terms of some kind of a Taylor expansion. Now, the case, it might happen that the Hamiltonian depends on time, but the commutator is 0 at different times, then the only difference is we just replace this h times d delta t by an integral of h over your time. And probably the most complicated case will be when the Hamiltonians at different times do not commute. We didn't really discuss it. We will see a very similar example when we study perturbations. And then we have our operator. We should better talk about its eigenkets. Well, the easiest way to find the eigenkets of one operator is if you know some other operator which commutes with it. If you find the eigenkets of that operator, and assuming there is no degeneracy, in that case, the eigenkets of that operator A is also the eigenket of your operator H in this case. And so that is one way of determining what the eigenkets should be. Once you determine the Hamiltonian eigenkets, writing down the operator, the Hamiltonian operator, is just trivial, as we had seen in our first weeks. So if you have an operator, if you know its eigenvalues, if you know its eigenkets, this is your operator in our space. Of course, in this form, it's again a formal definition. Let's say it doesn't look like anything we can work with. But you see, nevertheless, you can if you have the Hamiltonian, you can write the time evolution operator in terms of this Hamiltonian operator. Again, it has basically identical form. You have the energy eigenket, energy eigenbra, and the corresponding eigenvalue of the time evolution operator. You see, time evolution operator is not Hermitian, so eigenvalues need not be real. So this is not a real number. But time evolution operator is unitary. So if there is an eigenvalue, the eigenvalues has to have unit norm. So you see, these are just phase factors. Their magnitude is just 1. These are the eigenvalues of those unitary time evolution operator. And once we know our time evolution operator, we basically can calculate the time evolution of any ket you like. Just you have your ket, write it as an expansion of the energy eigenkets. And then the time evolution of that initial ket is just multiply each one of the energy eigenkets by the corresponding phase factor. So that will allow us to determine how the state evolves in time. And something else that will be important for us will be the expectation values, because in experiments, most of the time what we measure is just the expectation values of operators. But since we know how the ket evolves in time, we know how the expectation value should change in time. And it just turns out that any expectation value can be written as the sum of oscillating terms. And the frequency of the oscillating terms is related by the energy differences. And one special case was, we will meet it quite often, when our ket is an energy eigenstate to start with. Well, since it's an energy eigenstate to start with, in time, the only change it has, you see here, if alpha is an energy eigenket, there is a single term in that sum, and that term just acquires a phase that has a unit magnitude. And if you look at the expectation values of any operator in that state, in an energy eigenstate, although our state is changing in time by acquiring this phase, the expectation values do not change. So it's a state, basically, which doesn't change in time. When we measure any observable in that state, it doesn't really matter at which time we are measuring it. The averages will always be the same. And we call such states stationary states. Stationary states are basically states in which the expectation values do not change in time. And we know that energy eigenstates are such stationary states, not their superposition. And then we looked at an example of a spin in a magnetic field. So it basically has, this is something should be familiar from electromagnetism. So it's just the magnetic dipole moment times the magnetic field. In the case of spin, the magnetic dipole moment is proportional to the spin. And so if you have a B field in the magnetic field in the Z direction, your Hamiltonian is just proportional to SZ. So since we know the energy eigenkets of SZ, we know the energy eigenkets of the Hamiltonian. And E over here is nothing but the splitting between those two states. That's why I keep these factors of 2 over there. And then we looked at an arbitrary ket. It's just a superposition of our eigenstates. Well, we can just write down the time evolution. It's just insert these phases. And then we looked at some cases of the expectation value of SZ. It just turned out to be constant. Well, that is mainly because the Hamiltonian commutes with SZ. That's why we will see how the expectation value of any operator is related with its commutation relation with how the time dependence of the expectation value is related with these commutation relation on Wednesday. And then we looked at the SX operator and also the SY operator. They just turned out to be the expectation value of the SX turns out to go as the cosine of some frequency times time, and the SY just turns out to be the sine times the same frequency, E over H bar, times some time. And basically it tells us that the expectation values of the XY component of the spin vector, the component of the spin vector perpendicular to Z is basically rotating in the XY plane. So if you start, let's say initially SZ is constant, so you have some expectation, some fixed SZ expectation value. It is determined by these coefficients A and B. Let's say if you are talking about only the expectation value, the vector formed by expectation value is just rotating around the Z-axis. This is what we will call the spin precession. This is basically the summary of what we had done today. Well, it depends. For example, if you have degeneracy, let's say Hamiltonian acting on state A is, let's say, E times A. Hamiltonian acting on B is E times B. Hamiltonian acting on any combination of A and B is equal to A times alpha A plus beta B. So as long as a ket is an energy eigenket, it's stationary. So here we have this superposition of two energy eigenkets. It is still an energy eigenket because those two are degenerate. So I wouldn't say that the superposition can never be a stationary state. I would rather stick with the definition of what a stationary state is. If you have an energy eigenstate, it's a stationary state. So under which conditions do you get energy eigenstates? Well, it might change. I mean, if there is no degeneracy, then the eigenkets, each one is a energy eigenket, and superposition is not. If you have degeneracy, then just superposition of those stationary degenerate states is again an energy eigenket, so the superposition is a stationary state.
Peki bu çözdüğümüz örnekte Hamilton'u en son işte bir esnek şeklinde yazdığımız anda o son yazdığımız line bizim Hamilton'la esnetin komut ettiğini söylüyor.
Well, you see, mu is a constant. B is a constant. So if you just calculate H with Sz, this is equal to minus mu B Sz, Sz. Well, constants I can always take out of the commutators, Sz, Sz. Any operator commutes with itself.
Peki son olarak aşağıda arbitrary bir ket yazdığımızda A ya da B ikisinden birisi sıfır olmalı, stationary olduğunu. Burada degeneracy yok deyip başladığımız için o zaman.
Yes, yeah. In this problem, there is no degeneracy. You see, the energy eigenvalues are different. So if I want this superposition to be an energy eigenket, that's the definition of stationary state, either A or B should be zero.
Hocam ben de şeyi soracağım, biraz pragmatik oluyor ama yani spinle çalışırken hiç şeye girmemek daha mı mantıklı direkt notasyonuna? Yani matrislerle yapmak bazı işleri daha kolay geliyor gibi duruyor buradan. Yani aslında tarzda bir soru soracağım ama.
Well, you see, it depends. If you want to stick with the spin and not study anything else, you might be correct. I mean, you might prefer working with matrices. But if you want to generalize this, if you want to just have a framework that works in every circumstances, then this notation, not in every circumstances, you can write down a matrix to start with.
Tabii onun bir dezavantajı göremiyoruz. Biz sadece dümdüz matematik yapıyoruz matrislerde. Burada en azından arada bir state atlayabiliyor muyum onu görebiliyorum.
Well, you see, that is what our purpose is, understanding it, not just doing the mathematics. Okay, so see you on Wednesday.